是 Reimaging 公司的 J. Lee 先生分享重构 AI 计算，有请。
Good afternoon, everyone. Thank you for inviting us here to the talk. It's been exciting to hear everyone speak in the morning, and I think there's a lot of interesting stuff that's going on. But thanks again for hosting the event. One of the exciting things about being in this field is that you don't really have to explain to anyone why this field is important and where it's going, because there's a plethora of wide range of applications that people are excited about, and AI is one of the key enablers of doing all of that. However, today I want to dive a little bit more deeper into the fundamental blocks of what makes AI do what it does. And so we've seen a lot of applications, we've seen a lot of services and a lot of architectural things that have been going on. But today I would like to focus more on the fundamental building block, which is looking at the fundamental compute of what really goes into making this work. And so understanding AI compute at a fundamental level. And then lastly, just kind of capping it up with some of the highlights that we've been doing this year. So to introduce our company, first of all, we provide AI accelerated solutions. And I can dare to say that we do provide the best in class in terms of latency and also energy efficiency. But I'll go more into detail about what our main value proposition is later on. But the one thing that I want to really focus on is the word domain-specific acceleration, because a lot of companies that are working in this, it all boils down to, at a fundamental level, like accelerating in a specific domain. And to understand that, I think you really have to understand both parts of the equation, which is, one is what are you actually accelerating, how are you accelerating it? And number two, there is an issue of domain specificity that you have to really consider and actually solve. And without those two in combination, you won't be able to get an effective solution that works in the market. So let's dive in really quickly. So at a fundamental level, what is an AI processor? What does it really do? It's really a glorified calculator. It does computation, but at the core of that, it does something that's called a multiply and an accumulate operation. And so what you'll see in a lot of papers or a lot of chips is, if you boil it down, one of the main components is doing this computation at a massive scale. So you have a number of arrays that are doing this. But to further break this down, I want to look at looking at multiplication. So typically you would have multiplying a weight by some sort of activation or some sort of data input, and then actually adding a partial sum to that. And so at the top level of this, you have 3 memory reads to do the memory read, and then do the computation, and then you have to finally store the final result. So it requires a 1 memory write. So to do this operation, you have a compute in the middle, but you have memory operations before and after that. And so at a fundamental level, this becomes an issue of computation versus memory, and how do you actually optimize across that front. So again, looking at taking that basic building block, you're able to now assemble it into an array or some type of a massive array type of these units. Obviously, this is not the only thing that goes into your computation engine, but there's a lot of other things that go into it. And then you also have to worry about, there's not only just these types of simple multiply and accumulate operations, but there's also other very specific nonlinear functions as well. So how do you actually incorporate that into your compute fabric or logic? And so this compute fabric becomes a little bit heterogeneous at some level, but ultimately it's some fundamental core that's massively scaled up. And then, like I said before, with that compute engine, now you have to solve the memory problem. So on top of that, you have to layer in a lot of very high bandwidth memory operations to be able to pull out data in and to pull data back in and to do the memory writes. And so how are you able to efficiently do this? So this requires on the chip having a very high interconnect memory fabric and a very high efficient network on chip type architecture, but then also because of memory costs and memory hierarchy, you have to be able to do off-chip memory interfacing as well. So this becomes a total solution in terms of not only on-chip but off-chip memory bandwidth as well. And so let's say you have that solution, then even building further on that is you have an accelerator card, but to do it across multiple cards, now you actually have to worry about multi-card communication. And this becomes, at this late stage, more about it's fundamentally still the same issue, but you also have to add in like network costs as well into this. And so as you begin to sort of scale this up, it requires a very delicate balance between computation, memory, and then networking. And so this will be very domain specific to your to the application or the service that you're looking at. But beyond this, let's say we have this type of hardware solution. Now you're able to actually have to scale this up into look at the entire software stack that goes on that. And so with starting from the left, you have your hardware solution, but now you have to really be able to translate it all the way up to your actual AI models that are on the far right. And so in between there comes a huge, massive software layer that has to take these models, translate them back into something that the hardware can work with. And this requires a massive innovation as well at the software level, compiler stacks and different things that go on there. And so this really becomes, at this stage, a domain problem, because you can not only do typically general purpose processors or general purpose compute engines, you really don't have to worry about what goes on top of it. But for domain-specific accelerators, this becomes a full stack problem that you have to worry about. And so looking at the problem from the entire domain, crossing different hardware and also software boundaries becomes a very critical issue. And so this type of architecture is common, and it's pretty much the baseline for pretty much every AI accelerator solution that you'll find out there in the market. And so it becomes, how do you differentiate between these? How do you optimize between these boundaries? How do you balance the delicate balance between memory and also computation? And there's a wide variety of different tweaks to this, and also different approaches of how you can actually achieve this. But in terms of today's talk, I would want to mention one quick thing about the theme of the talk, which is building an open ecosystem and open ecology, which is, I think it's very critical that there's been a lot of work on the far right side in terms of getting AI models, having a common framework that a lot of developers can use. But on the bottom side, and even more so in the middle layer, there's not a whole lot of open standards that have been promoted or have been collaborated on. And this is partly because of the complexity of the problem is too difficult that you have to have a very hard optimized solution for that. But moving forward, I think one thing that it'll be interesting to see is that the industry comes together and brings together a more collaborative effort in this front that actually accelerates not only development, but also deployment of these solutions, because otherwise it will be very hard to speed up the development process as well. And so to cap it off, I talked a little bit about the compute, but then there's also memory, and then at the end there's also network. And so looking at it at a domain level, this also differs depending on your solution. So some networks will be more inclined to be more compute bound, whereas others are more memory bound. And so I think with the launch of ChatGPT last year, and even in transformer models in general, require much more massive memory bandwidth. And so the problem has become less about being compute bound, but more about being memory bound. And so we're seeing that with the release of ChatGPT and also other hardware solutions that have been coming out recently. And it's becoming there's more effort in terms of integrating in more high bandwidth memory for these. But then if you look further beyond that and looking at other scaled out or scaled up solutions, then this becomes also a network problem. And so I think a lot of different companies that have worked in this, primarily NVIDIA and other companies, you look at their portfolio of how they progress over the years, it's been, you eventually have to do everything. You start from computation, but you eventually bridge out to memory, and then you also have to look at networking issues as well. And so to do this entire thing is a very domain-specific problem that we have to solve. So coming back to one of the first slides is, so what is in Rebellion's main value proposition? So we actually focus specifically on inference. And to do that, looking back at some of the computation elements that I talked about, this allows us to actually optimize out a lot of stuff that we do not need, for example, for training. So we can optimize out some of the memory reads and writes as well. But then also looking at the other end of that is, what do we do with it? We want to actually achieve the fastest speed in terms of inference performance. And so we have optimized our entire solution to be one of the fastest inference engines out there in the market. And so with that, what kind of market are we serving? There's basically two different directions that we can go with this. The one on the left is something that we've started out. The company was first founded upon this market, which was looking at high-frequency trading operations. And this required a very latency-critical operation and had a very limited sort of application space, but it was very intriguing, and it was also a very nice fit for us because the metrics were very clear, and there had to be very highly optimized solutions. And so we initially focused on this. Um, but with the advent of ChatGPT and other things exploding, obviously, like looking at data center workloads has also been a very interesting and a very unique space. And so we've also sort of used the same core technology, but have been able to scale that up a little bit more. So the one on the left requires a little bit more smaller scale and chip. The one on the right, as you move forward, depending on your workload, you have much more massive networks that you have to work with. But if you think about the service level requirements, it still requires very fast response time from the end user. And so you need to still have a very fast, performant, and energy efficient solution to compete in this field. And so large language model is obviously one of sort of the premier sort of end targets for that. But underlying is the same core technology, and we were able to scale up depending on the needs of the market. So with this in mind, one of the things that we have really optimized is looking at having hardware level flexibility, hardware level optimization, but adding on software level flexibility. And we were able to achieve that by redesigning from the bottom up our core instruction set architecture specifically geared for deep learning problems. But also understanding that in able to work with the existing machine learning frameworks, you do have to have something that is very compatible and very easy and swappable with existing tools. And so we've been able to do both hardware optimization as well as seamlessly integrating that for the software stack. And so on this slide, I'll talk more about this on the next slide, but just a number of different technology solutions here, but I want to just quickly highlight just a couple things here. And the thing is that in terms of one of the AI inferencing benchmarks, which is called MMPerf, which was released, which we submitted to this year, we've been able to demonstrate that we have very high, very good performance in terms of latency. And I think for the vision task, it was ranked #1 in our category. But we were able to do that with less compute capacity. So you can see that in terms of compute capacity, it's comparable or even less than our competitors, but we're still able to get better numbers. And so this translates into having a very performant chip, but using less silicon to do that. And so that also translates favorably for energy efficiency as well. So moving on to some of our highlights and picking up on the previous slide is that we did submit to MLPerf this year, and we've been able to achieve very good latency numbers here. One thing I want to point out is beating the GPUs, I think, is pretty much a given for most AI accelerators because you're highly optimized for this space. But what was very encouraging for us was that we were able to beat out other AI accelerators in this space as well, which demonstrated that we do have the technology to drive very latency critical applications. And so having built on that, another key highlight this year was that our chip that was geared towards data centers came out late last year. So essentially starting from the earlier January this year, we were able to build up our entire solution and be able to ship it out for cloud data centers. And so just within even just a span of 5 to 6 months, we were able to rapidly bring up our hardware solutions, build our software stack upon that. And this is still ongoing work, but we were able to support more than 200 plus AI models here, which includes a lot of the more recent transformer models, including T5, and also even stable diffusion. We've been able to do some demonstrations there, but also being able to accelerate a number of core operators within the TensorFlow or PyTorch framework as well. We've been able to we continue to keep expanding that as we keep advancing our software stack. So that's been a very rapid development on our side, and a lot of great effort from our team. And so having built on that, we were able to ship out to KT Cloud data centers this year in May. And essentially, we were able to ship them out and serve them as a public NPU compute instances in the field. And so we have a limited number of customers that are sampling them right now, and we're continuing to expand on this in October and also in November this year as well. But also there are plans for expansion as well into well into next year. And lastly, just looking at how do we go beyond this at this point. So I think it's very encouraging to know that on the left side, looking at sort of the customer side, there's been a lot of engagements in doing a lot of different proof of concepts that are in progress. But There's a generic sort of software stack that I think most customers can use, but then there's also, we do a lot of customized tuning as well for specific models that sometimes customers have. And so there's been a lot of work with some of these customers here that we're looking at very customized software solutions that can just even tweak out more performance from our existing solutions. But on the right side, you also need to have a very strong supply system or supply chain to do this. And so one of the great advantages is of working in Korea and having a startup in Korea is that we do have one of the largest, one of the best foundries in the world, notably Samsung, and also being able to leverage an ecosystem that's built around that entire semiconductor supply chain is very critical for our operations and actually helping us in terms of getting down our margins as well. So we've been collaborating with Samsung, and I think these are also recently released in the press just a couple weeks ago. But we have ongoing partnership with Samsung to build our next generation chips, but also even looking with other companies outside of Korea. And to really increase reliability and chip performance as well. And so that's been an ongoing thing with IBM Cloud as well. And obviously, this is still in the very early stages of the field, but we do believe that not only just showing great performance, but also being able to scale up and scale out and showing reliable operation across the entire front is very important as well. So with that, I would just like to conclude and just kind of thank our partners. We've been able to have a very strong working relationship with KT, and thanks to their great partnership, we've been able to demonstrate some key pieces in the data center. But this is a very exciting time, and I believe that the future of AI it is really here. It is now. It is a present thing that is ongoing. We are excited to build on top of that. And so with that, I thank you very much.